Hi, I'm Campos and I'm going to talk about automated synthesis of modular manipulators structure and control for continuous tasks around obstacles. Imagine that you have a set of building blocks composed of 1-degree freedom modules, links of several lengths, and tube adapters to connect module and link, and you want to combine these pieces into a serial chain manipulator able to accomplish a high-level task, for example, to paint these rows. Now, there might exist uncountable different ways to put these pieces together, but how can we automatically choose one able to accomplish the task? That's what we address here. We developed a framework to automatically synthesize correct by construction manipulator structure and controls from high-level trajectory specifications. Here, the task is a 2D trajectory composed of parameterized curves that we call shape primitives that can be of the type line segments, circles, and arcs. The task might also include obstacles to be avoided and constraints on the base of the manipulator. Now, previous works also consider continuous trajectories as tasks. However, they discretize the trajectory and they use the selected points to find the design and controls to reach those points. Now, even if the design is able to reach these points, there are no guarantees that it can complete the original trajectory. Consequently, a discrepancy between the original and the resultant trajectories might occur. In our approach, by only allowing trajectories composed of shape primitives, we do not require the discretization step, ensuring that the original trajectory is followed. We formulate the problem of finding a manipulator structure and its controls as a constraint optimization, in which the task is encoded as a set of constraints on the manipulator's kinematics. In our formulation, the decision variables are the position of the manipulator at certain points of the shape primitives. For example, for a 2-degree freedom manipulator in a task that is only a line segment, the decision variables will be the position of the origin and the elbow of the manipulator, such that the end-effector is able to reach the extremity points of the shape primitive, as well as the closest point of to the origin on the shape primitive. The consistency of the structure is guaranteed by imposing that the distance between two consecutive modules and the module in the end effector is equal to the link length. We also impose that the origin of the manipulator is inside the restricted area specified by the user. Due to the arrangement of the pieces, self-collision might occur if the end effector gets too close to the other links. Thus, we add a constraint guaranteeing that the end effector respect a minimal distance to the other links. Collision avoidance is performed in steps. First, given the candidate structure of the manipulator, we calculate an over-approximation of the swept volume, and we add constraints imposing that there is no intersection between the swept volume and the obstacles in the environment. However, this swept volume over-approximation might be too conservative, resulting in no solutions when there might exist one. Then, we proceed to calculate a less conservative approximation of the swept volume. Then we add a verification step guaranteeing that the motion is collision-free. Summarizing, from a high-level task specification, our approach outputs the planar manipulator structure and its controls able to accomplish it. Now a few demonstrations. Here we have the painter rows task. In the left, the simulation, and the right, we have the constructed manipulator performing the task. Here, the manipulator is required to wipe off some material on a table. Again, in your left, the simulation provided by our approach, and in your right, the corresponding manipulator. Here, the manipulator is required to clean some spilled coffee on a table. A limitation of our work is that it's not complete, meaning that we might not find a solution even though there might exist one. In future work, we want to develop automated ways to increase the likelihood of finding a solution, as well as providing feedback to the user regarding infeasible tasks, and add 3D tasks in our approach. Thank you.